So today we will be solving the problem detect a cycle in an undirected graph, but this time we will be solving this using the BFS algorithm. Yes, in the previous video we did learn about how to solve this problem using the DFS algorithm, but over here we are going to use the other traversal technique that is known as the breadth first search traversal technique. So just in case if you do not know about this technique, I have already made a video on this technique, so go back and watch that video and then you can come back and watch it again. So you're given this graph. Now it's not two graphs, right? It's a graph with two different components. So if I ask you, does this graph contain a cycle? So you will be saying yes, because even if this component doesn't contain a cycle, this component does contain a cycle. If any of the components in a graph does contain a cycle, I can say that there is a cycle, right? So you just need to detect a cycle. So as we know that every graph will be stored in an adjacency list. So at first let's draw the adjacency list. So the adjacency list of the graph will look something like this, right? So now if you have seen the BFS traversal video, what is the first step that we do? We always consider a visiting array. So let's draw a visiting array of size 11. So this will be the visiting array and everything will be marked initially as unvisited, which means 0, right? What's the next step that we always do in the BFS traversal? We know that there can be multiple components, right? So what we do is we always run a for loop so that it calls a DFS for every unvisited node. So the for loop will run from 1 to n, where n is the total number of nodes. Over here n will be 11. So we know that if this node is not visited, right? If this node is not visited, it means the node I is not visited, I will call the BFS traversal. Now over here, what will be the BFS traversal doing? It will be checking if there is a cycle. So I can say this time I'll call a function cycle BFS or cycle BFS check, something like that, with the node I, which will simply check if there is a cycle or not. If there is a cycle, I can say I can return a true. Now again, why this? Because if any of the node is unvisited, I'm going to call a traversal. That means I'm traversing for a new component. And if in that component I do find a cycle, that means the entire graph is a cycle, so I can simply return. So that's how we are going to do. We're going to run a BFS for every component, and if we find a cycle in any component, we simply return a true. So this will be our logic. It's just that we have to decide what modifications we have to do in the BFS traversal so that we can detect a cycle using the BFS. So the modifications in the BFS have to be discussed. So let's understand the thought process. What is the BFS traversal? It's breadth first traversal. So at first you traverse here, then you traverse here, then you try to traverse here and here simultaneously adjacent nodes, then you traverse here and here. Right after that, when you traverse here, right after this, 8 will try to traverse to its adjacent node, that is 7. And since it tries to traverse to its adjacent node 7 and it finds that that has already been traversed, which means there is a cycle. Now had there not been a cycle, that means this node, this edge would not have been there, then 8 would never have found its adjacent node to have been already visited. So this will be our thought process. If any of the adjacent node has been visited previously, then I can say that there is a cycle, right? For this 8, the next node was 7 that was visited previously. So I could say that there is a cycle. So let's see how we will be doing this in the DFS traversal. So at first, the value of I will be 1. So what we do is we take the value of I as 1 and we check if 1 is unvisited. So we see that 1 is unvisited. So that means we are going to call a cycle BFS, right? So we call a cycle BFS with the value 1. So let's call the cycle BFS check or whatever your function name is with the node value 1, right? How does BFS works? It initially takes a queue, right? It initially takes a queue. Now this time we will modify the queue. In the normal BFS traversal, we did just put the node in it. Over here, we are going to put the node as well as the previous or the parent node. I'll tell you the significance of the parent node as we move forward in discussing the modifications in our BFS traversal. So initially, I can say over here the starting node will be 1, and I can say 1 doesn't have any previous node. It doesn't has, right? So I can put a -1 saying that the starting node will never have a previous node because this is the point where I start traversing. So I will surely not have anything on my back. So I'm pointing it by -1. So this will be an initialization. You'll take a queue which will have a node parent and you'll insert 1 comma -1, and at the same time please make sure that 1 is marked as visited, and you'll have this visited array. After this, you're going to run a while loop, right, which traverses for all the nodes. So the first node that you get is 1, and the parent node or the previous node is -1. Now let's check out what are the adjacent node for the node 1. So the adjacent node is 2. So you check out, is 2 visited? No, 2 is not visited. So obviously it's not a cycle because not previously visited. So what you do is you take this 2 and put it into our queue. Now, when you put it into the queue, what will be the previous node? Now you have traversed from 1, now you're trying to go to 2, right? So that means the previous node will be 1 because you came from 1. So the previous node will be 1. So you put this 1 into your queue. So once you have done this, please make sure you mark 2 as visited also. So does 1 have any further adjacent nodes? I cannot see. So the traversal for node 1 is over. Next time, again you check which is the topmost value at your node. So at your queue. So the value that you get is 2. What's the previous node? 1. So now if you check out what are the adjacent nodes of 2. So the adjacent node of 2 is 1. So you check out, is that visited? Yes, it is visited. But can you say that it is a cycle? No. Why? Because this one which is visited is actually the previous node. So from the position you came, that is what it is giving as an adjacent node. So that's not a cycle. That's just the previous node. That is why it's visited. So I will ignore this. Next I check out 4. Okay, is that visited? No. Let's mark it as visited and let's put that into our queue. 4 comma, what will be the previous node? 2, because 4 came from 2. Do we have any further adjacent nodes for 2? No. So the traversal for 2 is also completed. Right next, what you'll do? You'll have the node value 4. So let's take that out. So when you take the node value 4 out, you have the previous node as 2. Let's check out the adjacent nodes of 4. So the adjacent node of 4 is 2. I see, is that visited? Yes, it's visited, but will you call it as a cycle? No, because that's a previous node. And obviously if you came from a previous node, it's bound to be visited. So you came to 4, so if the previous node is 2, that's an adjacent node. So it's visited because you came from it. So I can ignore this 2 and I'll not put it into our queue. So I can say there are no further nodes for 4. So the traversal for 4 is complete. So once you complete the traversal for 4, you see that the queue becomes empty. That means you have done the BFS traversal for the node starting with 1. That means this entire component has been visited. But did you find a cycle? No. So this function is going to return a false, right? And whenever it returns a false, it gets a false. It means this component did not have a cycle. So we are going to move across to the next component to check for a cycle. So the I will become 2. Is 2 visited? Yes, because this component was already visited. Next time I will become 3. Is 3 visited? No. So if 3 is not visited, I go to inside that and call the cycle BFS function. So the cycle BFS function will now call 3, right? What were your steps in the BFS traversal? You always declared a queue. And since you have modified the BFS, this time the BFS will contain node and parent. So initially you have the node 3, and since this is the starting point, I can say that the initial parent will be -1. And what is the other thing that you did before starting on with the traversal? Please make sure you mark 3 as visited. So you have done that, right? Now what will you do? Now the traversal starts. So the traversal starts with the value node 3 and the previous as 1. So let's check out the adjacent nodes of 3. So the adjacent nodes of 3 is 5. So you basically check if 5 is unvisited. Yes, that's unvisited. So let's visit 5 and make sure you put that into the queue. So 5 comma 3, because 3 will be the node from where did 5 come. So 3 is visited. Now you have made sure that 5 is also visited. So the traversal for 3 is over because 3 doesn't have any further adjacent nodes. Now it's time to take the next guy out, that's 5. So let's take 5 out. So if you take 5 out, the previous node will be 3. So let's check out for the adjacent nodes of 5. So the adjacent nodes of 5 is 3. But can you say that it's a cycle? No, because 3 is again an adjacent node which was actually previous. So it's bound to be visited. So next node you get is 10. So you check out, is 10 visited? And you see that 10 is not visited. So what you do is you mark it as visited and you take that 10 and you put that into your queue data structure. So if you put that into your queue data structure, it will be 10 comma 5, right? What about the next adjacent node? It's 6. So do you see 6 as visited? No. So please make sure you mark it as visited and you put it into your queue. So 6 comma 5 does go into your queue, right? So put that into your queue. What's your next step? Obviously your next step will be to check if there are any further adjacent nodes, and you see that there are no further adjacent nodes. So the traversal for the node 5 is over. Next time you get this node 10. So let's check. So let's take out the node 10. So in the previous traversal 6 and 10 were visited, right? So the previous node for 10 is 5. So let's check out the adjacent nodes for 10. So the adjacent nodes for 10 is 5. Now you see that 5 is visited, but will you call it as a cycle? No, because 5 is the previous node itself. So the previous node is bound to be visited. So there is no need to put it into the queue. What's the next adjacent node? 9. Is 9 visited? No. So please make sure you mark it as visited and you take 9 and the previous node will be 10 for 9, right? So you put it into your queue. So you visit 9 also. Are there any further adjacent nodes for 10? No. So you just complete the traversal for 10. Now you get the next guy, that is 6. So let's write 6. So you have a 6 and the parent of the previous node for 6 is 5, right? So let's check out the adjacent nodes for 6. So for 6, the adjacent nodes are 5. Again, 5 is the parent node. That is why 5 is visited. So it's not a cycle. It's the previous node. So it's not a cycle. Next adjacent node for 6, that is 7. Is 7 visited? No. So you please make sure you mark it as a visited and you put it into your queue data structure. So 7 comma 6 is what you put in the queue. So 7 is also visited. So are there any further adjacent nodes for 6? Because 7 is also done. No. So I can say the traversal for 6 is over. Now let's check out what's the next node. So the next node is basically 9, where the previous is, or the parent is 10. So let's check out the adjacent nodes for 9. The first adjacent node for 9 is 10. 10 is already visited, but 10 is the previous or the parent node. So you cannot call this as a cycle. So you will not take this node into consideration. Let's check out the next adjacent node. It's 8. So this guy 8 is actually not visited. So please mark it as visited and you please make sure that 8 is being taken, right? So you take 8 and the previous node for this 8 will be 9. So that means this 8 came across this guy. This 8 came across this path. Understand? It came across this path, right? So are there any further adjacent nodes for 9? No. So the traversal for 9 is over. Next is the most important step. So you see that the next value is 7, 6. So please make sure you write this. So node of 7 and the previous is 6. So for 7, what is the adjacent node? 1 is 6. That's very obvious because 7 did come up from 6. That is why the previous or the parent node is 6. So I can say that's an adjacent node. So that's why I cannot say that it is a cycle. But the next adjacent node for 7 is 8. And you see that 8 is already visited. But 8 is not the previous node. So if 7 had a traversal from this side, how did 8 got marked as visited? That means someone would have traversed from this side, right? And it would have marked it at visited. Now, since you're traversing from this side and you came across to 8, that means there is a cycle. There is a cycle. That is what BFS will tell you, because you traverse breadthwise in this direction. Someone else did traverse breadthwise in this direction. And ultimately, both of you did reach this same guy 8, which means there is a cycle in your component, in this component, which ultimately means there is a cycle in your entire graph. So you can say right over here, the moment you see that this 8 is not equivalent to the parent and that's marked as visited, you can say there is a cycle, and you can directly return a true, saying that there is a cycle. So this guy gets a true and this returns a true, which means there is a cycle in your graph. So the stuff over here is very simple. If in any of the component you get a cycle, it means in the entire graph you can say that there is a cycle. So that is what I have done over here. So the thought process is very simple. We try to maintain a previous, so that if we are following a path and in the next we get a node which has been visited by someone else, that means there is a cycle, right? So let's talk about the time complexity of this algorithm. I can say, since the BFS traversal takes big O of n, because there are n nodes to traverse, so I can say that the time complexity will be big O of n. And what about the space complexity? I can call the space complexity as big O of n in general terms, because I'm using a visited array, I'm using a queue, but it's near about n. So I can call the near about time complexity and the space complexity to be big O of n if we use the BFS traversal. Now you must be thinking, if both the algorithms have the same complexity, which one to use? Again, it's completely on you. You can use any one of the algorithms to detect a cycle, either the BFS or the DFS. Now it's time to discuss the C++ as well as the Java code for this cycle detection using BFS. So let's discuss the C++ solution to the algorithm. So you know how to store a graph in an adjacency list. And let's assume the number of nodes is n. So I'm basically calling a function isCycle with the total number of nodes as well as the graph that is stored in the adjacency list, and telling the function to tell me if there is a cycle in an entire graph. So this function will initially declare a visited array which will be marked as 0. What's the next step? I know in any of the components, if there is a cycle, that means the graph has a cycle. So I run a for loop and I will be calling check for cycle for every unvisited node. The stuff that I did explain while explaining the algorithm, right? So I basically call the check for cycle. What are the parameters that you will pass? You will pass the starting node for which the BFS will be called. Along with that, make sure you pass on the variables like the number of nodes, the graph, adjacency list, and the visited array. So if this BFS call returns a true, that means the component has a cycle. So you're going to return a true, right? So I write a boolean check for cycle. And this does take the starting node for which the BFS will start. Along with this, it takes the number of nodes. This is not required, but I've just passed it on. And the adjacency list as well as the visited array. Now what I do is, I declare a queue, right, of pair, which stores the node as well as the previous or the parent, whatever you want to call it. Now I make sure that the node where I am starting is marked as visited. And I'm also inserting the initial starting node with the previous as -1. So these were the initializations that I did in the modified BFS. Right after that, you're going to traverse till your queue is not empty, or if you find a cycle. So what I do is I take the topmost element in the queue, because that is what we will be traversing for. So you get the node as well as the previous. Right after that, you traverse for all its adjacent nodes. So let's traverse for all its adjacent node. So what do you check is, if that adjacent node has not been visited yet, that's a very simple task. You mark it as visited, right? And you put it into your queue. Simple as that. But what if that's visited? What if this if is false? That means the adjacent node has been visited. And if the adjacent node is not among the previous one, what does that mean? Someone else would have been visited. Someone else would have visited that. if your adjacent node is visited and that's not equivalent to your parent or previous, it means there is a cycle. So you return a true. So you can return a true the moment you find it, and the BFS will be over. But if you complete this traversal, as you saw in the example for the first component, the queue will become empty. In that case, the component doesn't have a cycle. So you're going to return a false. So this is how your modified BFS will look like, and it will give you an answer if there is a cycle in a component or not. So this will be your entire code. If this returns true at any moment, it means there is a cycle. If it would have checked for every node and it did not find a cycle, you'll lastly come across to the line number 45 and you'll return a false. So this will be the code for C++. I'll be leaving the code in the description below, right? So do check it out. So let's discuss the Java solution to the logic that we did discuss. So since we know that a graph can be stored in an adjacency list, and you know the number of nodes is v, so I have written a function is cycle, which is gonna take your graph in forms of adjacency list, and it will take the number of nodes, and this function will check if there is a cycle in the entire graph, and it's gonna return a true if there is, and if there is no cycle, it is going to return a false. So initially what I do is I basically create a visited array and make sure everyone is marked as unvisited, which means false. Now the next step, I need to check for every component, because I know if I'm checking for a graph, in that case, if any of the component contains a cycle, that's going to return a true. So as already discussed, I run a loop from 1 to the number of nodes, that is v, and if the node is unvisited, I basically call the DFS, I basically call the BFS, the modified BFS, the check BFS, the check for cycle BFS, whatever you want to name it, you can. And I just pass in the starting node along with the graph and the visited array. So this is my function, which takes the adjacency list, takes the starting node for which the BFS is called, and takes the visited array. Now what I've done is, as you did see that the queue was containing two elements, so I've created a class of node which contains the first and second. Basically, first will be the node, and the second you can say as the parent, right? So it does contain that. So you know what is the initial step? The starting node has to be inserted into the queue, and the parent of that will be -1, because that's the starting node. So you insert s comma -1, and whatever is the first step, that's marking it as visited. So please make sure the initialization steps are completed, of putting the starting node into the queue and marking it as visited. Now what was the next step? You kept on traversing for every node till the queue didn't become empty. So let's do it. So what you do is you get the first guy, that's the node, and the parent, right? You just get the first guy from the queue. And once you've got it, please make sure you remove it, because that will not be required for your next iteration. So once you've removed, traverse for all its adjacent node. Adjacents dot get of node will give you the list of the adjacent nodes, and you can for each loop in that. So what I get is it as the adjacent node. So if this node has not been traversed, the task was very simple. If the node was not traversed, we always marked this as visited, and we did put that into the queue. Now how will you put that into the queue? The node will be it, and the previous node from where it came will be node. So please make sure you put them into the queue. But what if that adjacent node is visited? If visited it is true, it means this adjacent node has been visited. There can be two options. Either it's the previous node, then means no cycle. But what if it's not the previous node and visited? It means it would have been visited by someone else, which apparently gives you an indication that there is a cycle. So I can simply return a true, which says me that there is a cycle. Someone else has marked that visited. So I return true. But what if this never gets executed? Like in the example you saw, the first component went on, and ultimately the queue become empty after all the nodes were traversed. So in that case, this while loop will get over, and you can return a false saying that this component did not give me any cycles. So basically, if any of the times this returns a true, it will ultimately return a true. But if the entire for loop is executed and it did not find a cycle for any component, so at the end you can return a false saying that there was no cycle. So this will be it for the Java code. I'll be leaving the link of the code in the description below. So I hope you have understood the entire explanation as well as the code. So if you did, please make sure you like this video, and if you're new to our channel, don't forget to subscribe to our channel. So in the next video, I'll be discussing the solution to detect a cycle in directed graphs using DFS. So let's meet in the next video.
Whenever your heart is broken,